And today what we're going to do is be talking about something called the DTFT. And I'm going to try to do this. This is in your book on page 397, I think, 396 and 397. I want to tell you this. He talks about what's called the Z-transform first, but I prefer to do the DTFT, and I'll tell you why. The DTFT is the discrete time Fourier transform. We've just done the Fourier transform, so it makes sense to go into the discrete domain right from there. The Z-transform is really the discrete Laplace transform. And here's what I mean by that. Now guys, I'm going to try to make this as clear as possible. This can be confusing, but this is where we're getting closer and closer to real signal processing, digital signal processing. Remember, that's where we're working towards. So, when we talk about the DTFT, what it really is something that takes the Fourier transform and it operates it or it applies it to a discrete signal. So first I have to create a discrete or sampled signal. And I'll call mine S sample of T. I'm going to simply do this. I'm going to just make it, this isn't exactly the way the book does it, but you'll appreciate this. I'm going to say it's simply going to be a series from n equals minus infinity to infinity of x of t times delta of t minus nt, capital T. Now that t is the sampling period. Y'all understand that, class? If you just take a look at this, it's going to bother you a little. I have a summation that goes from minus infinity to infinity, and I've got x of t here, and then I multiply it by delta of t minus nt. I'm not going to do the convolution formula, but this will work. Now, if you look at this, what is really happening? X of t looks something like, maybe it looks like this, right, versus t. What this does is basically a bed of nails, right, that is just going to get a coefficient in front of that at, this is really x of t, and all these points right here would be x of nt. Now, I know that delta function technically goes to infinity. Just think of the value of x of t as the scale factor. The x of nt is the scale factor in front of the delta. How many understand this, class? So I've got to create something, a sampled signal. This is the easiest possible way to do it. Just say take an infinite series of delta functions and multiply it by the actual signal, you can get the sampled signal. Now, one thing I'm going to tell you, this thing itself, because the delta function really only has values when t is equal to nt, correct, class? And n is an integer. So I can say that this is equal to a summation here from n equals minus infinity to infinity of just x of nt times delta of t minus nt. Do y'all grant me that one? Everyone? Right? All right. Now what I've done is I've gotten rid of the argument t here. Some of you won't like it, but nevertheless, I've got rid of it, right? Now keep watching. Now we apply the definition of the Fourier transform, x of omega. The definition says of anything, when I take the integral from minus infinity to infinity of x of t, and now it's not going to be x of t, it's going to be the sample version, so I'm not even going to bother putting x of t in there. I'm going to put x sampled of t, or just replace it with this, times actually the summation here, n equals minus infinity to infinity of x of nt times delta of t minus nt. It's going to be that times e to the minus j n omega naught, or j, sorry, not omega naught, think of it, j omega t dt. Do y'all see that, class? Are you agreeing with me there? How many do? All I've done is to, instead of putting x of t here times e to the minus j omega t dt, I just replaced it by the definition of the sampled signal. Do y'all follow me? Now, keep following me on this one. You'll notice that this integration is in t and the summation is in n, correct? So I can change the order of operators. I can do the sum, I can basically do the integration first and then the summation. Does that make sense to everybody? Sure. So I can do it this way. I can say that this is really equal to a summation, n equals minus infinity to infinity here. And then it would be of the integral from minus infinity to infinity. This is done all the time, so you might as well get used to this. Of the summation of n equals minus infinity to infinity of x of nts here times e to the minus j, excuse me, times delta of t minus nts right here times e to the minus j and omega naught, or j, pardon me, j omega t dt. Y'all follow me on that, class? Only thing I've done is change the order of operations, right? Correct? How many see this right here? Now the summation, or the integration is inside the summation. Now just watch this. You see how this integration is on dt? But, oh boy. Yeah, that's because I actually messed up. This actually should be this. I'm sorry about that. Thank you. Got something in the back of my mind. It happened at lunch. So anyway, I'll forget about it now. Y'all with me on this? Now, follow me on this part. In radar, we put TS as the sample period. This is just T. It's the same thing. I'm sorry. T is the sampling period. A lot of times it's T sub S in my radar class, and in another class that, well, actually, the other book uses T sub S, but that's just the sampling interval. Does everybody follow me on this one? Now, this is the key part right here. If you agree with this, that this is an acceptable definition of a sampled signal, and it is, then this is the definition of a Fourier transform, and when I go here, you'll notice the integration is in T, right? But this argument is in capital T, so I can take that in front of the integration. Just watch me. I'm going to go ahead and do it. I'm going to put right here, x of n capital T. Follow me? And now you're going to see how this actually works. I have an integration from minus infinity to infinity of delta t minus n capital T times e to the minus j omega t dt, correct? What do we know whenever we integrate a delta function? What does it do? Pulls out the value of any neighboring functions at the point where the delta function goes to infinity, correct? Which happens to be n capital T, correct? And that means this really can be replaced by a summation of n equals minus infinity to infinity, and now it becomes x of n t, and t is the sampling interval, times simply e to the minus j omega n capital T. Does everybody follow me on this? And this is where we define the DTFT, right here. But we do one other thing. We allow this. We call it n omega t simply becomes n capital omega, or capital omega here will be equal to just omega times t, the sampling period. We box that, that's important. And then the next thing we do is we suppress that t inside the argument of nt. Really, the function is a function only of n. T is a scale factor. Do you all follow me in that, class? When I look at this, I could just as well say that this function right here, right? Even though it's a function of t, admittedly, really what this is a function of n, right? Because only at integer values of n and at the value capital T does it actually have a meaningful, something besides 0. Do you all see that? So what they do is this. They define that, and this is the fundamental definition, they say that x of omega is the definition of the DTFT, and this is in our book, and it's equal to a summation from n equals minus infinity to plus infinity of just that, x of n they're going to suppress the t. It will only be a function of n. The t is implicit. It's sort of like when you do your problems in circuits, and you have 10 at an angle of 30 degrees as the excitation voltage. They assume you know the frequency omega. Do y'all follow me in that class? It's an assumption. Same here. X of n, and it's going to be times e to the minus j n omega. Now that's the definition right here of the DFT that's used. But by the same token, it's related to the actual Fourier transform, where capital omega is small omega times capital T, where T is the sampling interval. Do y'all follow me? I got a few things to say about this. That's a summation, right? This is important. When you look at this, you'll notice that this argument is omega, right? Now, because of that, every time I add omega, if you add 2 pi to it, don't you get the same value? If you have e to the minus j n, quote, omega plus 2 pi, don't you have the same value as e to the j or minus j n omega? Do y'all follow me? It's periodic in 2 pi, which means that this thing will have a meaningful value from minus pi to pi, or from 0 to 2 pi, and it will always repeat itself up and down the capital omega axis. Do you understand that? The only real information we care about is over one period of 2 pi. So we care from either minus pi to plus pi, or from 0 to 2 pi. We don't care about the infinite axis. Do y'all follow me in this class? This is very important. Remember, with the DT, or when the actual Fourier transform, the information spanned from minus infinity to infinity. You cared about everything, right? Here, the entire, you could say, frequency spectrum is compressed over a range of 2 pi, and then it just repeats itself over and over. That's what happens to x of omega. Does everybody understand that? And it's because it's sampled. That's the reason. Now, with that in mind, we're going to do a few. I'm going to give you the inverse too. You're going to see a lot of things happening here. One of the questions that should come to mind is, why do we care about this? And the real reason is because in the real world, you do not have a continuous signal. You have sampled signals where you have discrete values at discrete points in time. And this transform is applicable to that kind of information, and it's very useful. All right, so with that in mind, now that's the actual forward DTFT. The inverse, if you want x of t, this is actually synthesis. This one you like, is simply 1 over 2 pi, the integral from minus pi to pi of x of capital omega times e to the j n capital omega d omega. Now, I want you to take one look at that and just contrast that to the actual inverse for the Fourier transform. If I want to this is actually x of n, pardon me. I'm putting x of t. This should be x of n. Here, x of t, the continuous time, inverses 1 over 2 pi, the integral from minus infinity to infinity of capital X of omega times e to the j omega t d omega, right? Correct, class? What do you notice different? Well, really, it's pretty much the same exact thing, except for the range here. It goes from minus pi to pi. Here it goes from minus infinity to infinity, right? But if you look at this, they're basically very close, right? They're similar. So it has the same basic trends. We'll spend more time on the inverse later, but I just wanted to put that up there. Now I have to do this. The next logical thing to do is actually calculate the DTFT of a few standard functions, I think. And by the way, in your book, I hope he has a table of these. Yeah, he shows us on page 398 some of the typical ones. And I'm going to tell you, some of these functions, they just look a little funny, just for the record. They're not as easy to see as other ones. But the properties is what we'll make use of to get the transforms of bizarre things. All right, next thing. All right, so let's let's see, what's the first function you think I'm going to choose to get the DT of? And I'll put the definition. Just take a guess.
Delta t.
Delta function, right. Delta of n, actually. And here's something I have to define differently, so you need to pay attention here. When we talk about a function, delta of block at n, they always use square blocks to indicate discrete time. And n is an integer value. 0, 1, 2, 3, stuff like that. Could be -1, -2. But it's always a discrete value. It's an integer value. This is equal to 1 only when n is 0. And it's equal to 0 else. Now, unlike the delta function that we had before, remember delta t went to infinity, but the area under the curve was 1, right? It was a needle, basically. It went to infinity, but it was very thin. The area was constant, right? Here, the value of this is 1. This is important. This is the discrete time delta function, the definition of that. It's different than the continuous time. Now, if you want to calculate the dt ft of that, I'll put the definition right here. I know that x of omega, right, is equal to the summation n equals -infinity to +infinity of the function x of n, right? Remember, it's a sum, not an integral. So this function is delta of n times e to the -jn omega, right? Y'all give me that? What is that just by looking? Where does the delta function have a non-zero value at n equal? 0. And what is the value of the other function next to it evaluated when n equals 0? 1. So it's 1. And lo and behold, isn't that the same thing of a delta t in the actual Fourier domain class? Isn't it 1 also? So that's nice. I guess we could start doing this. We'll make a table. This is going to be x of n. This is going to be x of omega. He has these. But for this one, the first one is delta of n. And that has a value of 1. And that's common, right? Now, the next thing usually is done is an exponential decay. All right, we're going to take a to the n, not e to the a, or e to the, remember before we had e to the -at? I'll show you the relationship. We're going to do this one next. I'll try to keep this up going as long as I can. Before you had x of t was equal to something like e to the -at times u of t, right? Now, what we're going to have is something analogous to this for x of n. X of n is going to be equal to a to the n times u of n, and I didn't tell you what u of n was, so I'm going to right now over here. U of n, right, is really equal to, simply it's equal to 1 for n greater than or equal to 0, and it's equal to 0 else. So it's just like the u of t function, exactly like the u of t, only it's evaluated at discrete points, n equals 0, 1, 2, 3, 4. Do you all see that, class? That's all it is. U of n and u of t, basically the same thing. Now, when you look at this, actually, I'm going to do something. I'm going to take, instead of a, I'm going to make that a b for a reason. When you look at this, right, how could I make these two things equal to each other? Now watch. If I take a look at e to the -bt, that's equal to a to the n in terms of the actual relationship I'm looking for. Isn't it, class? Y'all follow me on this one? I'm trying to actually say, if I sample this, how would I get this value a to the n? That's where I'm going, right? Well, take a look at this. I sample it at e to the -b times nt would be equal to a to the n, because remember the sampling interval is n capital T, right? The t is the actual sampling period or sampling time. Understand, class? How many do? I'm going to see what I'm getting. Well, what do you see happening here? Well, if I have that, right? If I take a log of both sides, I get -bnt here is equal to n times the natural log of a. Don't I, class? Isn't that right? Log of both sides? Log of e is just the argument of e, correct? Or the exponent of e, correct? And what do you see here? That means the n's can go away. And log of a is equal to minus b times t. And that means a would be what? E to the minus b times t. Do you all see that, class? How many do right here? So if this is continuous time and we sample that signal at t, then the a that would be involved, that would be represented there, would have the value of e to the minus bt. How many see this? This is important you do. The book does not point this out. It assumes you see it. Are you with me on this, everyone? Now, the one thing about this you got to know, if a is greater than 1, this thing is blowing up. Follow me? If a is less than 1, it is going to be going down, and it has a finite summation that you'll see. This is very, very important. So the value of a defines when the actual DTFT exists. And I didn't say this yet, but for this DTFT to exist, it means that the summation of just x of n has to be finite. And I'll spend more time on that later. That's not really a focus right now. But it's just like the Fourier transform. Remember, for a Fourier transform of a signal x of t to exist, what did you know has to happen? With the integration of the magnitude of x of t had to be less than infinity. Do y'all remember that, class? Vaguely? Well, that's important because you couldn't, remember, that's the power of Laplace. We could get the Fourier transform of functions that we couldn't get Laplace transform could get the Laplace transforms of functions we couldn't get the Fourier transform for. How many remember that? That's one of the powers of Laplace. All right, now, so we're going to go ahead and get the transform of this function. Now here I have to rely on something I gave you guys a while ago about, do you remember when I put up, you've got that, so I'm going to use this part of the board. I put up a couple of relationships of summations. One of them was, I said, we did this with discrete time Fourier transforms, we did this for convolution, discrete convolution, but I didn't really spend a lot of time on this. I'm going to remember that I said if you have a summation from n equals q1 to q2 of a function a to the n, all right? How many remember at least me putting that down? If you don't remember what it is, how many remember that? 1, 2, and everybody else, 3, 4. And I was like, I'm clueless. I've never seen it. In a court of law, you'd never prove. Anyway, this is an important one. I'll tell you how I did it, just to bring it back. This one you probably start remembering now. If I had this and it went from 0 to capital N, that's an infinite series, right? I mean, it's a series, not an infinite. Do y'all agree with that? I'm starting at 0 for a reason. All right, what does that actually equal to? It's a, right, to the 0, or 1. I mean, just put down 1. Plus a squared plus dot 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 plus a to the capital N. Do you all follow me? Yes. Thank you. Now, what I'm going to do is say if that is a to the n, if that's what the series is, then if I have 1 times that series from n equals 0 to n times a to the n, and I minus it times a times that series of a to the n, where n goes from 0 to n, what I'm actually going to get, the first series here is just going to be what? 1 plus a squared plus dot 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 plus, and then it's going to go all the way up to a to the n. That's the first series, right? The second series is going to be, it's minus, and then it's going to be, well, it's a times 1. So it's a plus a squared plus a cubed plus dot 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 plus a to the n plus 1. Isn't that right? And this is equal to what? It's 1 minus a times the infinite, or times the finite series from n equals 0 to n of a to the n. Is it not, class? Please just take a look at this. What I'm showing you is a way to actually reason yourself through some pretty complicated stuff that'll come your way in probably random. I think that's where you hit it first. But in your senior level courses, you're going to be asked to reason out things that have a lot to do with series stuff. Now, what does that mean? What does this go to? Just look at it. Well, 1 appears here, right? Is there a 1 over here? No. A appears here. Minus, is there an A? Yes. You see, everything gets wiped out except for what? A to the n plus 1. So it's minus A to the n plus 1. And then, if I take that and I divide it by 1 plus 1 minus A, now I get the summation from n equals 0 to capital N. This is a powerful one here. And I'm going to go ahead and just say one thing about this. I'm going to make it more general. If this is just, and I like to use the symbol Q because the book uses this all the time. If I put Q1 to Q2 here, we could prove this one too. This one would go to, it would be equal to A to the Q1 minus A to the Q2 plus 1 over 1 minus A. So the only thing that happens is now the superscripts of A, instead of being 1, A to the 0, now it's going to be A to the Q1. It's where you start the series summation. And you stop at A to the Q2, the upper limit, plus 1. Follow me? How many see this right here? Now, why is this so useful? We're going to see in about 1 second. And I'm going to do that over here. So now, we're going to go ahead and say, well, what is going to be this? Well, first, let me do one other thing. I'm sorry, I'm not trying to be disjoint, but what do you think the transform of delta n minus, say, a was, where a is going to be an integer over here? Just what was it before a continuous time? A phase shift, right? Do you all remember that? Phase shift? Well, in discrete time, if you take a look at this one, I would say x of capital omega for this guy would be equal to the summation, right, of n equals minus infinity to infinity of delta of n minus a times, in this case, it's going to be e to the minus j omega n. What is that value? Just take a look. Well, where does the delta function turn on? At A. I could use m there too, but at A. So what is this going to be? E to the minus j omega times A, isn't it? Let me put that down. So delta of n minus a is just going to be e to the minus j times omega times a, or put the a out in front. It doesn't matter. Do you all follow me? Show of hands here. Let me see that. I should have done that right after. Now I'm going to go ahead and do the summation, or I'm going to do a to the n. We're going to get the transform now of a to the n. This is the next one. So there's 1. And then we're going to do, a to the n, u of n. And this one's real important. This one crops up because this looks like you're sampling a decaying exponential, which occurs all the time. All the time. Follow me, class? Work with me on this one. All right, now here, and I'll go right here and do it. Now I put in a to the n times e to the minus j omega n, right? And I want to use that series form. What's my next step, anybody? I know you see it. What do I want? I would like to get something to the nth power, because that something is like my a, isn't it? Over there in that discussion, correct, class? So now I need something to the a power. Maybe, how about I use b here so it doesn't confuse you? I'll use b to the n. All right? It's just like a, only that way you can look over there at that formula and not be confused. Do you follow me, class? All right, what is this going to be? This is going to be a summation here from n equals minus infinity to infinity. And what do? We could say it's what? It's b times e to the minus j omega, isn't it, to the nth power? Take a look at that. Do you all agree with that? A to the n times b to the n is what? A times b to the n. Isn't it, class? Show of hands here. Let me see this. Are you with me? I always worry about people that are looking at me with a scowl. I don't know if they think that I'm lying or what, but I'm not trying to deceive you. I'm trying to be as clear as I can. Do you all see this? So this looks like my what? My a over there, doesn't it? And what does that mean this goes to? It's 1 minus all that stuff to infinity, and really, since b is going to be assumed less than 1, it's just 1, isn't it? Over what? 1 minus b times e to the minus j omega. Do you all see that, class? Let me go ahead and put the way the book does, and here I'm going to use the a to the n. The transform of that will be 1 over 1 minus a times e to the minus j omega. I need a little more room.
Are the limits of the sum supposed to be 0 to infinity?
Well, the u of n makes it. Sorry, I didn't put the u of n here.
Oh.
U of n will get rid of the,
Yeah.
that lower limit. I'm sorry about that. Whoever said that's right. It starts, it's got to have a u of n there, because if it didn't, then it wouldn't have a finite summation, be an infinite value. Follow me? So if you take a look at this, this is what the book has, and it also writes it this way. What it does is multiply top and bottom by e to the minus j omega, and it gives you this as e to the j omega over e to the j omega minus a. It does it both ways. There's a reason it does it the other way. All right, but for now, this is the one that's important. I'm going to show you what this looks like. Now remember what I mentioned, that the Fourier transform exists from minus infinity to plus infinity. When we sample a waveform, we take that entire frequency axis and we crunch it down from minus pi to plus pi. Follow me? Everybody? Now this is important, what I'm going to show you next. So now, one of the things that happens is this. When we actually look at this, I'll call this the Fourier transform of that. I'm just going to call it x of capital omega for now. When I look at the magnitude of x of capital omega, by the way, you'll notice this is a complex number, right? It has both magnitude and phase. Do you all see that, class? This is important. Magnitude and phase. I'm just showing the magnitude. And I'm going to go from minus pi to plus pi. All right, from minus pi to plus pi, you start whenever you're doing a function, trying to get an estimate what it looks like. You start when omega is 0. When omega is 0, you have e to the 0, which is 1. And so it's 1 over 1 minus a, right? Now that's actually the peak value. This is going to be a value of 1 over 1 minus a right there. That's the peak. And as omega is increased, really is what happening is this is getting what? Closer and closer to minus 1. If you think about it, what is e to the minus j pi? Anybody? Isn't e to the minus j pi minus 1? If you're not used to thinking about things, and what I'm going to show you, start, because it'll be very helpful. Whenever you think about something where you have e to the j, any angle at all, think of it as a unit vector, right? And this is going to be the real axis. And this is the imaginary axis right here. That's 1, that's minus 1, there's j, and this is minus j. What's happening is this angle right here is theta. It's getting bigger and bigger and bigger and bigger and bigger. By the time it hits pi or 180 degrees, that's minus 1. Follow me? How many see this? It's going from here, or strictly real, to strictly imaginary, to strictly negative 1. Now, when it's negative 1, what happens? Now I have 1 over 1 plus a. Do you all see that? That's the smallest value. That's down here. 1 over 1 plus a. And how does it get there? Something like this. And it looks like a bell right there. All right? This is a really, it's an important one to understand. And then, forever after I go past pi, from pi to 3 pi, if I went that way, let's call this 2 pi, call this 3 pi, then it would repeat itself. Follow me? And it does the same thing up and down the axis. Just does that. If you can understand what I'm saying. All right, so that's what it looks like. Now what happens when the value of a gets close to 1? What do you see happening? Say it's 0.001. No, I'm sorry. Say a is equal to 0.9999999. Then this goes to a 0. That's my point. Follow me? Because then you'll have I mean, sorry, not a 0. This right here goes to infinity. I'm sorry about this. This will go to infinity. That's what my problem was. All right? It'll start skewing. You just have to be able to see that. Whenever you get an extreme peak, it means the value of the decaying exponential, it's decaying very slowly. And all the power is really at the low frequency point. Now, just think about this. What did the exponential function look like? If you just thought about that for a second, what did e to the minus at u of t look like? 1 over a plus j omega, right? Well, what's the value when omega is 0? 1 over a, right? Our value isn't 1 over a, it's 1 over what? 1 minus a. There's a similarity though. It's proportional, you might say, in scale of 1 over a. Now, when you look at this, the omega there is something that as the frequency goes up and up, it has more of a pronounced effect. And if you actually plotted the magnitude of this, I think you can see it. What you would have is a value of 1 over a, if you just put magnitude of x of omega here, and you would get this kind of a curve, wouldn't you? I mean, you can imagine, it's an extended bell, isn't it, class? Now, I can't do this easily, but I can show you, if you go and look at the compression effect, you basically took the entire axis from minus infinity to plus infinity and confined it from minus pi to pi. And that's really what happens when you sample. All right, now there's a couple of slight things that are a little different, but that's generally the way I think about DTFT. It's just like a Fourier transform, and now all the frequency, all the possible frequency are compressed between minus pi and pi. That's the way I deal with that. All right, that one. Next. And this is the real power of this is analysis. And I'm going to show you in time in the next couple of lectures how you can actually take the information from a DTFT, and then we use something called a DFT. It's a truncated series DTFT, and compare it directly to a Fourier transform. So you can take a look at something and you can then scale it directly so that it compares exactly to a real Fourier transform of a sampled signal. And that's a very powerful tool, and you'll see why. Mainly because you have a good hand. You've seen the Fourier transform. You know what to expect intuitively. All right, now that's A to the n. The next one that they like doing is a pulse function. Remember, with Fourier transforms and continuous and discrete time Fourier transforms, you can have functions that have non-zero values below n equals 0, right? For negative values, and this is important. So do you remember the pulse function that we had before, or the rect function, right? Well, here we have another function, and this is the way it's defined. In the book, I want to tell you one thing. He may say something that I don't like. I'm sure he does. Unfortunately, he doesn't give you this function. Oh, he does. There he goes. Yeah, there it is. He's got it number 9. It's rect of n over capital N. And let me just put down the formal version of his. His rect function of n over capital N is equal to u of n plus capital N minus u of n minus 1 minus n. All right, so now we got to talk about this. What does this look like? Let's come down and start at minus n, make this plus n. And then don't worry about the increments for now. All right, and this is the function, rect of small n over cap n. He's going to use rect. I like pulse. All right, work with me on here. You'll notice that n is not this span. This span is 2n. Everybody see it's actually 2n plus 1 because there's 0 there. Do you follow me, class? Everybody? Now keep watching. When does this one first turn on, this one? N equal minus n, right? So now basically here we have a 0 and here we have a value of 1. And it's going to stay there until what? Take a look. Until what? until this argument. When does this one become, where's the transitional point when? N, right, small n minus 1 minus n equals 0 is the transitional point, correct, class? Isn't that right? The step after that, then that's going to kill this one, right? But this is the point, I'm sorry, this is the point where it kills that one. I'm sorry, I didn't say that wrong. So where does that occur? That's n equal what? 1 plus n, correct? 1 plus n is here, right? When it's n, right, it's still what? Off. This one hasn't turned on yet. Do y'all follow me? But then at n plus 1 it turns on. And the reason he does it this way is this. This thing is symmetric about the origin. Do you all see that? You have the same number of values this way as this way from the origin. And how many values do you have? You have 2n plus 1, because 0's there. Do you all see this, class? And this is what's called, this is the discrete time pulse. I like saying, I use this symbol. I call it P, and then I put 2q here. I always have 2 times q of n, and 2q right there would be equal to the actual span, which is 2n. All right? Do you follow me on that, class? You can use the rect function too. I don't want to ever confuse you with the symbolism there should not be confusing. I will probably either graph it or use the rect of n over small or capital N, because that way you all know that it's symmetric, and the span on the positive side is n, the negative side is n. Follow me? Now we got to get the transform of that. We've got to go ahead and get the DTFT of that. So let me go ahead and do that. What's that? Where did I drop that? Didn't I?
Need another rag?
Wait a second.
Look over there by your book.
Bro. Thank you.
I didn't know how far it was going to go. There's nothing heavy in it.
By the way, when you ask a student to throw something and you don't define what it is, you may get hit with something really bad. All right, let's do this. Remember what the fundamental definition. I know this is fresh, and I know you haven't seen it before. But the fundamental definition of x of omega is what? The summation n equals minus infinity to infinity of x of n times e to the minus j n omega. Now, I didn't ask this. Maybe I should stop right here. We have to get a test in, right? At some point. I don't know, a couple of people have approached me. Who was supposed to remind me that didn't? Now, I'm not going to admit to it. Anyway, I've asked at least one. Didn't I ask you? No, it wasn't you. 2 people in here, I think. And neither one is going to fess up to it. I actually forgot. All right. What I'd like you to do is this. On Friday, the whole class remind me, first thing, to get a vote on when you'd like your test. Now, this is up to you. I could care. I'm going to tell you one thing. It's my experience. Monday, usually the test scores are the highest because you have a weekend of studying like this. Worst time, Friday. Usually the worst scores. Just because it's the end of the week, you're beat up with labs, who knows what. You're ready to just die. Anyway, Wednesday is somewhere in between. I don't care when it is, but I'm giving you the freedom to choose in the next couple weeks, say the next 2 weeks, all right? So from Friday, you got 2 weeks. Figure out when you want the test. You know your other tests, and what we're going to do, just listen to me. I'm going to take 3 or 4 dates, and we're going to vote on them. The top 2 will have a runoff, all right? And you can go ahead and politic all you want to your friends about how your dog's going to die if you don't see it, or whatever. What?
Spring break like a week out.
Yeah.
All right, you can have it after spring break.
Oh, okay.
You can have it before or after. Look, I don't care. I'm giving you the option. If you want me to be a bad guy, I'll just say it'll be the day before spring break. But I want to make sure that I give you the option. Is that fair, guys? If you want it after spring break, fine. If you survive. All right, let me finish this. Guys, oh, am I out of time? Well, I'm gonna finish it anyway. Now look, that's just one. You understand me? That pulse function right there? So when we take, if we want the actual transform of the pulse function I just put up there, the summation of rect of small n over cap n times e to the minus j n omega from n equals minus infinity to infinity, what do we do with this summation? There's one single thing we do. It's only going to go from where to where? From minus n to plus n, right? Because that's the only time rect is non-zero. It has a value of 1. And then we're going to eliminate rect. Why? Because we hate it. No, because it's only 1. So now this becomes n equals minus n to plus n of just e to the minus j n omega, right? Now, I'm not going to have time to do that, but you all see what a is there? A is what? E to the minus j omega, right? Go ahead and do good with that formula, and I'll pick it up there next time. I'm going to give you some problems. One other thing, I'm going to get 100 emails about this if I don't say something. Everybody's going to say, is there a quiz Friday? This Friday there isn't. There is not a quiz this Friday. But if I decide to take roll and there's not enough heads here, then anybody who's not here is going to lose 10 points. I'm fairness to everybody.